Okay, guys, just a quick recap of everything we have learned so far, guys. Wait, pay attention. All right, first part here, we learned about the effects of forces, right? The effects of forces was a very straightforward one. You either change the shape, size, speed, or direction only. This one was something very straightforward. Then the second part we learned about was very important about Hooke's law, right? Guys, I mentioned last week, guys, two very important things of Hooke's law. Shit, am I recording? Yes. Okay, the first one is definitely the formula F equals to Kx. Your K was the spring constant, and spring constant tells you the what of the spring again? What does the spring constant tell you about the spring? What's the units for spring constant again? Yeah, and because it is newtons per meter, if I have one spring that is 100 newtons per meter versus another string that is 200 newtons per meter, which one is the strongest spring? Yeah, the 200. You need to say the spring constant actually tells you the strength of the spring. The higher the spring constant, obviously, the stronger the spring, right? Then from this graph here, we are actually supposed to be able to define Hooke's law. You still remember how to define it? Hooke's law states that the force is directly proportional to the extension of the spring, provided that the elastic limit is not exceeded. Guys, always remember, if you have this graph here, you can define Hooke's law on your own, really, guys. Very, very important. Okay, right. Then after that, once we were done with that, we talked about the F equals to ma formula also, right? Whenever we talk about F equals to ma, the F is what force again? What's the full name of the F here? What force? Okay, for example, if I have an object here that is being pulled with 30 newtons and another force here that pulls it with 100 newtons, what's my F? 130 or what?
10.
Good, it is the 70. Why is it the 70? Because this is your resultant force. All right, guys, always remember, whenever we talk about F equals to ma, your F must be the resultant force and not just any random forces. It must be the resultant force, right? Then from here, we also talked about the two conditions, three conditions, right, for the forces. It will either have deceleration. This is when the backward force is greater than your forward force. For example, when you step on the decelerator, right? It will either move at constant speed or stationary. This is when the two forces are equal or back and forward, right? Like another example is like you sitting on your chair, like I mentioned last week. If today your chair exerts 500 newtons on you and you exert 500 newtons on the chair, you will be stationary, right? So there is no resultant forces. When there is no resultant forces, it will be stationary. Or alternatively, when your forward force is greater than your backward force, this is what we call acceleration. Right, lastly, we also talked about the three forms of resistance. It would be either friction force, most common one, drag, which is usually in water, and air resistance, which is obviously in air. Right, so it's solid, liquid, and gas here in this scenario here. Right, then after that, we left off here. We talk about circular motion. Guys, let's talk a little bit circular motion and try to understand how circular motion occurs. Today, let's imagine this is Earth, right? Let's say this is Earth. And then I have the moon. The moon usually circles around the Earth, right? Right, circle around the Earth here. Right, let's imagine this is the moon, this is the moon, this is the moon, and this is the moon. Now today we know for a fact that the moon is actually going to move in this circular motion here around the Earth. Do you know why it has a circular motion around the Earth? It's because it's affected by two specific forces. Number one, the first one here is the motion, the force due to its motion, right? We call it V. Okay, but there is a second force acting on the moon here. The second force is basically going to be the gravitational pull between the moon and the Earth. Every time there are two forces acting on an object, right, there will always be a resultant force in between the two forces. Okay, meaning to say the reason why the moon is at this position, is moving like this, is because there's one motion here and there's another gravitational pull here, right? And thus it has a resultant motion in this direction. Same thing for this one. So one force here, one force here, one force here, and one force here. And this gives the resultant force here. Okay. Now today, if you want to test this theory out at home, right, what you need to do is you pull both hands out, right? Just put both hands out and you ask one of your friends to pull one hand and another friend to pull another hand, you'll notice that as both hands is being pulled, your body will automatically lie forward. In fact, let's try it right now with Macy. No, you don't have a choice. For the name of science. Okay, I want you to put up both of your hands. Put up both your hands in both different directions. Notice where your heart, where your body is going. Pull in this direction here. Right, you see, your body will actually move forward here, indicating very important concept here. A very, very important concept is that when there are two forces acting on two different directions, your resultant force will always be in between them. Meaning to say, it doesn't matter if the object is being pulled in this direction and then this direction, this will be a resultant force. If the object is being pulled in this direction and this direction, this will be the resultant force. Okay, very, very, very important. I must know this because next one you're going to be asked about this really. But before we proceed on to that one here, guys, in your exam, whenever you see anything, once you identify that the question is circular motion, right? They will always ask the same question. Okay, the same question will be, they'll ask you, where is the resultant force acting on this object and where is the acceleration of this object here, guys? Whenever they talk about acceleration, guys, because this is gravity, right? I told you since many weeks ago that gravity is the same as acceleration, right? Whenever there is acceleration, it must be due to your F equals to ma, right? There must be a resultant force, right? So meaning to say, in your exam, guys, they'll give you something like this. They'll say something along this line. Like you see here, a car is traveling around a circular track at a constant speed as shown. In which direction is the resultant force of the car? Guys, as soon as you identify that this is circular motion, right? The resultant force or acceleration is always towards the center of the circle. It will never ever change. Okay, meaning to say, if the question changed a little bit, instead of asking for resultant force, right? If they ask about the acceleration of the car, bam, it's the same thing. It's always towards the center of the circle. Always towards the center of the circle. And in fact, right, if you want to be a bit more ballsy, right, what you can do is, right, you straight away see that this is a circular motion, right? You don't even need to read the question, right? For sure, the answer will be towards the center of the circle. This will be correct 90% of the time. Even if you don't read the question, straight away circle the one that is pointing towards the center of the circle, it will be correct 90% of the time. But there will still be a 10% chance that you'll be wrong. Okay, so in conclusion, don't be ballsy. Just read the question. Most of the time, the center of the circle is going to be the answer here. Okay, so if you look at this statement here, when the force acts 90 degrees to an object's travel direction, this will result in a resultant force in between the two forces. One force here, resultant force, one force here, resultant force. If the force continues to act at a 90 degrees to the motion, the object will keep changing its direction whilst remaining at constant speed. One more thing I want to highlight in this question here, guys. Even though I say that the speed is the same, I see this word, right? It has constant speed, right? Meaning to say at this point, the speed may be like 100 meters per second. Here is also 100, here is also 100, and here is also 100. But they'll say that the velocity is changing. Why will the velocity change? Because velocity is a... What is a velocity? Scalar or vector? The vector, good. Because velocity is a vector quantity, if my velocity is in this direction and my velocity is this direction, they are both different velocities because it takes into account its direction as well. So this is a different velocity and this is a different velocity. Even though the magnitude for the velocity is the same, so the speed is the same, right? But the velocity is not the same. And because there is a change in velocity, you could say that there is acceleration towards the center of the circle as well. Okay, so this is what happens when a planet orbits a star or a satellite orbits a planet. Okay. Yeah, a little bit like car drifting, right? You'll feel that there's always going to be a circular motion, a centripetal force towards the center of the circle, because there is acceleration towards the center of the circle. Okay, very important. This one here, 9 out of 10 questions, you'll get it correct. You must circle the one that is towards the center of the circle. Very, very important. Okay, before I move on. Anyone's got any questions they want to ask me about this one here? Circular, with regards to circular motion? Very, very important. Just in conclusion, circle the one that's towards the center of circle. Very easy. Okay, then next, this part here is the one that students, they hate the most, guys. Students generally struggle a lot in this chapter here. I will assume it's because their foundation is no good, right? But with me, you have a different story. Okay, now let's first and foremost understand what a moment is, guys. A moment, by the very definition, is the turning effect, guys, generated by something. For example, today, this opening of the door, right, is actually a movement as well. Why? Because a moment will always cause a turning effect. Now, a very, very easy example of moments is basically a seesaw. Okay, everyone's here played with a seesaw before, right? Everyone knows what happens if you stand alone on the seesaw, right? What's going to happen is this seesaw will start tilting towards this direction, right? This is what we call a moment. Okay, a moment will usually require three specific things. Number one, it must have a pivot, right? A pivot could be any supporting point. The pivot will not necessarily start in the middle. Pay attention. The pivot can be anywhere. Like for example, this door here, the pivot is all the way at the edge here, right? These hinges here are going to be the pivot, right? So from here, the second thing our moment needs is definitely the distance away from the pivot. Right? Have you ever noticed that if you stand further away on the seesaw versus sitting in front of the seesaw here, it will generate a different turning effect? Right? This is because the moment is different now. And the final part of a moment is definitely going to be the force, which in this case here will be the weight of the person now. Okay? Three things are must have pivot, must have force, must have distance. Right? From here, let's just imagine let's just imagine today the force here is 500 newtons. Okay, and the distance here, right? Let's for ease of calculation, make it 1 meter. Moment depends on two things only. The formula moment is equals to force times distance, right? Meaning to say in this case here will be 500 multiplied by 1, which is going to be 500 Newton meters. It is Newton meter because it's Newton multiplied by meters here. We say that this moment is going to produce a clockwise moment of 500 Newton meters. Okay, the moment will either be clockwise or anti-clockwise depending on where the pivot is. For example, if let's say I have a different person here, right, standing here, let's say also 1 meter away, right, and then this time his weight is like 700 newtons, right? Now obviously this moment here will be an anti-clockwise moment of 700 Newton meter. Understand what I'm talking about? This one here is very, very important. You need to identify whether it is clockwise or anti-clockwise in your exam. And because of that, I'm going to test every one of you guys here. And you guys are supposed to tell me whether it will be a clockwise movement or an anti-clockwise movement. Let's imagine today this is the pivot. Okay, let's go for an easy one first. Today, if I have a force here, right? If I have a force here that turns the seesaw, starting off with Macy, will this be a clockwise or anti-clockwise movement? This will be clockwise because it will spin according to the pivot mark, right? How about Lucas here? Lucas, if today I have a force in this direction, will it be clockwise or will it be anti-clockwise?
Anti-clockwise.
Oh, good, very good. It is going to be anti-clockwise because it spins in this direction, right? What if I have a pivot here, right? And then my force is in this direction. Neonica, will this be clockwise or anti-clockwise?
Clockwise.
Yes, good. It will be clockwise because it will spin according to this direction, right? Guys, pay attention now. Whether it is clockwise or anti-clockwise, it depends on where the pivot is. It depends on where the pivot is. Okay. So having said that, first and foremost, you need to understand for the moments is basically number one here, moment is known as a turning force around a pivot. It must have force, it must have pivot. It is the first thing. Moment is a vector quantity, therefore it has magnitude and direction. This one here will either be anti-clockwise or it could be clockwise. Okay, magnitude is obviously just the number in front now. Formula-wise, moment is force multiplied by perpendicular distance. Guys, pay attention. Whenever we talk about moments, guys, the distance must be perpendicular to each other. Meaning, say, if this is the force, this will be the distance. If this is the force, this is the distance. You'll notice that all of them are always perpendicular to each other, and the distance is always to the pivot only. It is to the pivot only. It will not go anywhere else. It must be to the pivot, force to the pivot, not force to force or force to another something. It is always force to the pivot. Okay, and from here the formula is going to be force times distance. Okay, guys, copy everything down and then do the 4 questions at the bottom. I'll give you guys 7 minutes. Oh shit. Oh. Remember, we took the line, clockwise, clockwise. F6. Shouldn't be 5, 6. Yeah, 5, 6. Yeah. And this
Very good. Let's see. I'm the right person.
Which girl? Xinyan? Yeah, Xinyan is joining. She's just away this week. So that's why I recorded for her. Okay, guys, are you done? Anyone not done with this first 4 questions yet? Let's go through the answers real quick, guys, going one by one here. Guys, if you look at this one here, they ask you to calculate moment, right? Moment is essentially going to be force multiplied by distance here. In this case here, it's obviously going to be 200 Newton multiplied by 0.25, divided by 4, right? So from here, you're supposed to get 50 Newton meters here. Easy, straightforward, right? Then the second question here is essentially the same thing, all right? You identify that this is your force and this is your distance. Moments is equals to force times distance. In this case here, with 5 multiplied by 0.5, which is going to give you 2.5 Newton meter. Oh, sorry, this is definitely clockwise. And this one, the one previously was going to be clockwise as well. All right. Was very easy. And after that, the next question here, you'll notice that this is in cm, guys. So you're actually supposed to change it into meters, which is 0.2. From here, yet again, movement equals to force times distance, which is going to be 10 times 0.2, which is going to give you 2 Newton meter. This would have been your answer here for question number 3, right? Quite straightforward as well. Then question number 4, oh, sorry, this is clockwise as well, guys. It's clockwise, right? Then finally, question number 4 here. Same thing, moment equals to force multiplied by distance, which is going to be 300 multiplied by 1.6, which will be 480 Newton meter. This time around is going to be anti-clockwise. Right. Anyone got anything wrong for these 4 questions here? Quite straightforward now, guys. Anyone got anything wrong from these 4 questions here? Okay, if there's no questions, next thing we're going to talk about is basically conditions of equilibrium. Okay, whenever you see the word equilibrium, guys, which is a very, very common question, right? To be equilibrium, you require 2 specific things, are conditions of equilibrium. Conditions of equilibrium. Okay, there's 2 conditions for it to be in equilibrium. Number 1, it must have 0 resultant forces. The second condition is for it to have 0 resultant moments. Okay, for 0 resultant forces is very straightforward, all right. 0 resultant forces is basically, let's imagine I have an object here, is being pushed by 100 newtons here, and then this thing is being pushed by another 100 newtons here. Right, obviously this one here has 0 resultant forces, right? So this would be in equilibrium. Alternatively, upward force equals to your downward force is also going to be in equilibrium, guys, as long as they cancel off each other, right? The first condition, 0 resultant force. This is the first condition. The second condition is going to be 0 resultant moments. Let's say, for example, today, same thing, the seesaw here. Okay, let's imagine today I have 2 friends, right? One friend that is like 500 newtons heavy, and another friend that is like, let's say, 300 newtons heavy, right? Today, if you just use your weight to play with this seesaw, it will definitely not work out. Why? Because if, let's say, I put the 500 Newton guy here, and I put the 300 Newton guy here, what's going to happen is, obviously, because this guy generates more moment, right? Then obviously this whole seesaw will start tilting towards one direction. it will tilt towards this direction instead. This is no fun. This is definitely not moments in equilibrium, guys. This is definitely not moments in equilibrium, because right now, if assume that this is 1 Newton, 1 meter, and this is 1 meter, right? Then this guy here would have generated 500 Newton meter clockwise, whereas this guy here would have generated 300 Newton meter anti-clockwise, right? So what can I do to make the moments the same? First and foremost, I know for a fact that I can't change the mass, right? The weight of the guy, unless I start chopping off his legs. So that is unchangeable already. So instead of that, what do? Is I start moving away. I move this guy away from the edge. Okay, well. I move this guy away from the edge. From here, I know that this is going to be something now. Guys, pay attention. From here, I know that in order for moments to be in equilibrium, the total anti-clockwise moment must be your total clockwise moment, guys. The first formula, guys, this formula is very important. From here, if let's say my anti-clockwise moment here is going to be 300 multiplied by 1, right? Then if let's say I have one guy standing here, I don't know how far he's standing away, but I know for a fact that he is 500 newtons. It's going to be 500 newtons multiplied by x, right? Right. From here, it is just a play of algebra, and I'll find that 300 divided by 500 would have been 0.6, meaning to say, in order for this guy to play in equilibrium with the red color guy, he can only stand 0.6 meters away, you know. This is how the seesaw can be in equilibrium. Now, the general formula for moments in equilibrium is going to be this, right? In most scenarios, especially if there is only one force and two forces here, right? If there's only two forces on the seesaw, most of the time, the formula will be F1 D1 equals to F2 D2. It will be F1 D1 is equals to F2 D2 here, right? Because this is the anti-clockwise moment, and this would have been the clockwise moments here. Very, very important, guys. I give you another example, or you tell me what to do. If today, same condition, I have a seesaw, right? But right now, this guy here is only 200 newtons, okay? And I got another fat guy standing on this side here, which is, let's just say, 600 newtons, okay? If this guy here is standing 3 meters away, let's not make 3 meters, let's say he stands 0.7 meters away, right? How far should this guy stand so that the seesaw is in equilibrium? First and foremost, we must apply the formulas, right? What was the formula I said just now? Moments in equilibrium states that the total, no, before that, that's the formula. The word equation first. Total what? Anti-clockwise moment must be equals to the total clockwise moment. From here, you can start writing down the formula, which in this case here will be F1 D1 is equals to F2 D2, right? From here, start applying 600 multiplied by x, I don't know how much is that, is equals to 200 multiplied by 0.7. Press that in the calculator. Find me how much will x be. Oh, 4.2, 6 some more. Nani, this guy must stand 4.3 meters away. You look at this diagram and you tell me, is it possible or not? This guy stands 4.3 meters away. 0.7 or 200 times 0.7 or. That okay, and then
600.
wait, didn't you just win the medal just now? 600 divided by 140, is it? Hello, it's 140 divided by 600, which is going to be how much? 0.233. If this guy is standing 0.233 meters away, then this anti-clockwise movement will be equals to your clockwise movement. And then this will be in equilibrium. You get what I mean? Anyone online don't get what I'm talking about. This is very important, guys. You must know how to do this one. Very, very important. Good. 100% absorption rate. Okay, if you have no questions from this part here, then the next part is basically going to be something like this. In your exam, most of the time they'll give you one forces, but sometimes they may give you two forces. Let's say, for example, I have a seesaw right now. I have one force that pushes here, one force that pushes here, and one force that pushes here. Let's just say right now, this is 500 Newton, and it is like, let's say, I don't know, maybe 0.7 meters away again. And then this thing here is like 1 point. Oh no, it can't be 1 point. It'll be like 0.2 meters away. Right. And this one here is, let's say, 300 newtons. Right. Let's just say this one last one here is going to be 600 newtons.
Then 0.6.
How far away must it stand from the pivot
Oh,
so that this thing is balanced? Guys, everyone try to do this question right now. I'll give you 3 minutes to attempt it, then I'll show you how to do it. Everyone do this right now.
Zero point 3.
0.3.
Oh yeah, it's like that.
No way it's going to be 0.3.
Clockwise.
Which one is clockwise and which one is anti-clockwise first? Identify it.
Ah, 800 0.9.
No. Why would it be 800 times 0.9? The total force is 800, and then the total distance is 0.9, is it? 0.9 is not the total. In fact, one is 0.7 and one is 0.2.
Both is.
Yeah. So you add both moments together.
Okay.
So instead of F1d1, it will be F1d1 plus F2d2 is equals to F3d3. Yeah.
Zero point 68.
0.68.
683.
Let's find out if it's correct. 0.683 meters away. Let's find out if it's correct. First and foremost, we identify, in order to tackle this question, we need to identify which ones are clockwise and which ones are anti-clockwise. This one here rotates like this, right? So obviously this one here is anti-clockwise, right? And this one here rotates like this, and this one here rotates like this, right? So means to say these two are clockwise, right? So from here, yet again, you write down the equation first. The equation will always be moments in equilibrium states that the total anti-clockwise moment must be equals to your total clockwise moment. Okay. From here, anti-clockwise got how much? 1 more, so it's F1d1 is going to be equals to your F2d2 plus F3d3 here. Okay, that being said, you can substitute the numbers in 600 multiplied by your x. I don't know how much is it, right? Is equals to 300 multiplied by 0.2 plus 500 multiplied by 0.7. Press this in your calculator. How much would this be? 350 120, so 470. 470 divided by 600. Oh, sorry, 16. My bad. 16. So it's 410 divided by 600. Right? Is that a correct answer? 0.683. Good. Very good, Macy. Lucas, Neonica, do you guys manage to get this question? Do you know how to do this or not? Or are you guys stuck at this question here?
I'm okay, sir.
Okay, all right. Okay, so this is how you're supposed to do it, guys. This is going to be moments in equilibrium. Always remember that this part here is the general formula. Don't just go like F1D1 equals to F2D2, because sometimes there could be more than 3 forces, right? So you're going to change the equation according to what you know. Okay? Okay, that being said, if you look back at the statements here, this is essentially everything I mentioned, just in more worded format, right? If you look here, in order to be balanced, the clockwise movements must be equal to the anti-clockwise movements. We say that the beam is in a state of equilibrium. The principle of moment states that if an object is in equilibrium, the sum of the clockwise moment about any point is equal to the sum of the anti-clockwise movement about that point. About that point means to say with reference to the pivot, guys, right? So obviously anti-clockwise movement equals to clockwise movement. Force times distance is equal to force times distance. This is only true if there are 2 forces, guys. If there's more than 2 forces, then it will be a different equation. But this is the general one first. Okay, copy writing down and then attempt the 4 questions here. Guys, you'll notice that question 1, 3, and 4 is quite straightforward and easy to do. Question number 3 is the brain teaser, guys. Yeah, 1, 3, and 4 is the easy one. Question 3 is the brain teaser. It's harder.
Why?
Oh, sorry. My brain is thinking about something else. Question 1, 2, and 4 is easy. Then question 3 is the brain teaser. Okay. Please copy everything down and then attempt the 4 questions. You'll need a little bit more time on this one. You're going to have 10 minutes.
Please, set the theme for your elements. On eight is 每个人当前，每个人也不是那个看人，现在为什么会是也要？No，
当时，
没有那个，好累，睡不着，今天睡不着。Yeah, drafting. But if it's on the opposite. Each three have to land in the we tell it to the Sorry, I feel garbage. But you also did my so and unfortunately.
这边强烈，
And the reflection of it's really comes out.
对吗？还有个东西，
就别的，就别的电视里看的，
哪里怎么会看出来？这是
你没有拼颜色啊，讲被看也有大概几十年时候嘛，
你要用你的 imagination 还有 critical thinking skills。
scary。
因为他的话可能都没有看到，后来就是到了学了就容易这样子。下一个并没有考虑，不，你要给我告诉你下一个 test 还有这个考虑你 special 的，没有人有话，我交给你。我是你的，基本没可以的。
I mean,是就是
10分是pass the common sense category is it 10分
爽，以前嘛不要的嘛，我人。
你知道那因为我是不能考试去的，这样子，要拿点什么？有力不行。
Guys, for question number 3, if you're stuck now, pay attention now. This thing here is a meter ruler. These indicators here, right, is not the length. It's just the marking of the ruler only. It starts from 0 and goes to 100. That's the only tip I will give you. Aaron, proceed on.
Oh, wow, that's stable. I will do it. Stress you.
Right.
No pressure is good. So one. Bye. Talk. 这边上网吃了没事，他就说，对呀，什么人呢？日本的香两个，两个人相同吗？你像他可以 voice 当然是可以，一开始我第一次我待在前面。我的第二个是就培养你到上的这个，我开始我毕业的时候，后面就会了，所以就问你，我是说刚刚怎么的？对。我没有。
Well, Joe, you ship out. What? How much do you get? Wrong. I don't think that you did the right working, so.
Neolika or Lucas, do you guys manage to do this question? Oh, 我弄了一个soundboard just for this moment. I'm so sad it actually didn't come up. Oh, I know why already. This was the reason why I was. Oh wait, but I don't think they can hear me right now. Hello? They can hear? Oh, good. I have this exact moment was for this. Oh God, hold on, make it stop. That's a bit too long, right? What the hell? Now back to this. Oh God, which one was the one again? Oh, this was the one. Wait a minute. Hello? Oh, okay, never mind. Back to this. Anyways,
I feel like they hear like
I think they are supposed to hear, but I don't know. I just set it up today only. The exact moment has come, but I was not prepared enough. But anyways, from here, you're supposed to do the first question, very straightforward. Anti-clockwise is definitely this one, right? So it's just going to be 20 multiplied by 1 now, which is going to give you 20 Newton meter. Straightforward, easy, nothing to explain. Clockwise moment is going to be this one, right? It's going to be 10 multiplied by 2 log, which is obviously going to be 20 Newton meter as well, indicating that they have both moments, meaning to say they are in equilibrium. Same thing for this one as well. James weighs 200 newtons, right? It's 200 newtons and sits 1 meter away from the pivot. If this guy is only weighing 100 newtons, how far must he sit away to be in equilibrium? It's basically 100 multiplied by your x lah. If you do your calculation here, your x is definitely going to be 2 meters. Very straightforward, very easy, right? Question number 4, also very straightforward. The red car is 10k newtons. 10k means to say it's 10,000. And this yellow car is 9k newtons each, means to say the total is 27k newtons, right? Because there's 3 cars. Right. So from here, if you want to balance it out, it's yet again moments in equilibrium, which is going to be a force times distance is equal to your force times distance, which in this case here will be 100 multiplied by 300 cm is equals to 27. Sorry, not 100. It's 10,000. It's 10,000 multiplied by 300 cm is equals to 27,000 multiplied by your x. And from here, your x should be 111 cm away. Or you could change it into meters and get 1.11 meters away. Do you get this? What do you get?
I write at 9 instead of 27.
Oh, you didn't see there's 3 cars, man.
Yeah, I saw, but
You forgot about it. Eh?
yeah.
Each is 9 kilonewtons each here. Right, so you're supposed to get 1.1 meters away, or even 111 cm. Okay, and then finally, my favorite question. What? I swear to God, right? This thing here is like faulty. That's why it's not the perfect moment. Next week we come back, it will be a perfect moment already. Okay, but anyways, moving back here, right? This is my favorite question of them all. Okay, if you look at the question here, it says that the picture above shows a meter ruler and a force acting upon it. The F, find the F from the diagram given above. We are supposed to look for this here. First and foremost, I know that there are 3 forces here, right? So obviously the moments of equilibrium must apply, right? Moments in equilibrium states that the total anti-clockwise moment must be equals to your total clockwise moment. Yes, this here is anti, this here is anti, and this is for clockwise. Yes. So from here, F1 D1 more. First F1 D1 plus F2 D2 is equal to F3 D3 here. Okay, I'll give you 2 minutes to write everything down. Guys, Macy here has requested for her to do it again. You have 2 minutes, guys. For those who have not attempted it, I've given you the answers until this far already. I think you guys should be able to finish up the question. Let me know your answers after this. Well, you want to start doing also? 这样子你读完书过后你要做什么？现在你读完这边过后你要做什么？ Foundation 吗？啊
3.0.
In what? Yeah, it's 3.0. What do you want to do after this? After IGs, what do you want to do?
You know what?
Why?
The 20 cm, I didn't count the 20 to 50. I count 20 to 50. Sorry.
That's wrong. That's a very common mistake. Good. But yeah, the answer is going to be 3 newtons. Why is it going to be 3 newtons, guys? First and foremost, when you write F1, it's very straightforward, right? It's just 2 newtons, right? Then after you multiply by your D, guys, like I keep saying over and over again, the distance is always from the force to the pivot, not force to force or force to force or force to force here. All this, no, all wrong, right? It's always going to be the force to the pivot, which in this case here is going to be 30 cm lah, right? Because 20 to 50 in between is 30 ma. Then you plus with your F2, which is your F. I don't know how much is that, but my D2 is here, right? Which is essentially going to be 20. Is equals to my F3, which is this one, right? My 3 newtons multiplied by my distance here, which is essentially going to be 40, right? From here, after you've done everything, just press everything in the calculator. 60 plus 20 F is equals to 120. Then my F will be essentially 60 divided by 20, which is going to be 3 newtons here. And this is how we do the question number 3, guys. Very, very important. Anyone don't know how to do this? This is very important. Everyone understand what I'm talking about? Yeah. Anyone's got any questions for this part here? Okay, good. If there's no questions, then we move on. Okay, the final 2 parts here is basically learning about center of mass. Guys, as the name suggests, guys, center of mass is basically a point where all mass is concentrated upon, right? And specifically is going to be the center. For example, if I have a rectangle, right, the center of mass will be here. If I have a circle, the center of mass will be here. If I have a triangle, the center of mass will be here. If I have a square or whatever, all the ways the center of mass will be here. Even if I have a bar, guys, we assume that the mass acts here, right? If we have a bar, we assume that the mass acts here. Thus, the center of mass. If you want to relate center of mass, you can relate center of mass to reality with the most common one, which is tall people and short people. You'll notice that tall people is much more easier to topple over compared to short people. You're a stable girl, right? Right. Why? Because generally, the taller you are, the more your center of mass is away from the ground. Versus if you're shorter, your center of mass is definitely closer to the ground. In general, anything that is short and wide will be much more stable. The most common short and wide is the sumo wrestlers, right? You know, sumo wrestlers, as soon as they enter the court, they will start to squat down, right? Why do they squat down? It's not for fun or for a stand. It's because they're trying to lower the center of gravity. Then when they squat down, they start pushing the other sumos, right? The other sumo wrestlers away, right? It's much harder for you to be pushed when you're squat down compared to you're standing up. You can go play with this later on with your siblings. Or if you ask your mom to push you over. Standing up for sure, it'll be not as balanced, not so stable, right? Compared to squatting down. Okay, so from here, very straightforward concept. The center of mass of an object is a point where the average of all the mass on the object is supposed to be concentrated upon, right? The lower the center of gravity, the more stable it is. For example, comparing a Ferrari versus a double-decker. Obviously, you can see that the Ferrari can tilt like 75 degrees, no problem, right? But this double-decker, once it tilts beyond this supporting point here, this whole thing will start tumbling over already, right? This has to do with moments as well, okay? Because at this point here, the force is acting on the pivot. This force here is acting away from the pivot. So it creates an anti-clockwise moment. Oh, right. So obviously, the higher the center of gravity, the object becomes less stable, which in general is the taller people. Yeah, they're a little bit more unstable. For sure, very unstable. If I were to play rugby with him, right, I for sure find him to tackle because he's too tall, right? Very easy to tackle down, and he's a good time. Right? Yeah. So this experiment is basically just a way to find the center of gravity. If today we want to find the center of gravity for regular shaped objects, it's very straightforward. Just fold it in half, and we'll get the center. But if we have irregular shaped objects like this one here, it will require some work. And let me show you what that is with a video. Finding center of gravity. Okay, pay attention to this video. It's just 2 minutes.
The center of gravity of an object is a point where all the weight can be considered to be acting from. This can also be called the center of mass. For a simple uniform object, we can find the center of gravity easily by finding two lines of symmetry. Where the two lines intersect, that's the center of gravity. Even when we have an object that's hollow, the center of gravity is still where the two lines of symmetry cross. When we have an irregular object, it's slightly more complicated. We need a retort stand, a cork with a pin stuck to it, and a plumb line. I've made my plumb line from a hanging mass and a piece of string. I now need to make 2 points of suspension in this object. Hang it up by the first point of suspension. Hang the plumb line in front of it. Mark 2 points along this line and then join the points together. Hang the shape up by the second point of suspension and repeat what we've done before. Where the two lines intersect, that's the center of gravity. We can check if this point really is the center of gravity. If it is, it should balance on my finger like this.
Oh. You know, there's one guy in China that is damn good at finding the center of gravity. He can balance literally anything. Guy that can balance anything. This China guy is damn king. Seriously, he's the king of center of gravity. This one here. Watch this guy. Super king. It's all by finding where the center of gravity is. Then after that, countering the moments generated by it. What? No, he's just better at locating his center of gravity. Look at this. I don't think anyone can do that. It will take too much time. You know what happened there? Right now, at this scenario, the moment generated by this egg is the moment generated by these two bottles. All right. So as soon as I remove this egg, there will be an anti-clockwise movement in this direction. That's why you see this bottle topples in the anti-clockwise direction. Look again. Oh shit! You broke. I broke YouTube. Okay. So the reason why, right, he can actually balance this so far here is because he already found the center of gravity, which is somewhere here. The center of gravity will act downwards onto this pivoting point here. That's why it won't move. If we don't want to talk about center of gravity, if we talk about the individual weights of each part, this weight here will balance off this weight here. Sorry, this moment here will balance off this moment here. Oh shit. This moment here. And because of that, it will stay in balance. This guy can literally balance anything. Oh, definitely it takes a lot of time for sure. But he can balance literally anything. This is the king of center of gravity, man. I mean, seriously. Look at this. Literally. How can any normal person do this? I don't think any normal person can do this. But yeah, you get the idea, right? This is the power of center of gravity. Okay, so basically this last part here is basically what I mentioned now in the video, but it's just worded in format. It's worded properly only. To find the center of mass, we need a colored string, a clamp stand, and a piece of laminar paper. First, make a hole anywhere near the edge of the lamina, like what the video guy did. He put one hole here and another one hole here, right? The plumb line would then be suspended from the same point from the lamina hanging it. The plumb line will go down here. Draw a line of lamina where the plumb line passes. Draw this one line here and repeat step 1 to 4 on different edge. Step 1 to 4 on different edge here. Wherever the two lines intersect, that is essentially where the center of gravity is already for any irregular shape objects. In fact, right, when you guys go to school, you see some boys, they like to spin the book, right? The reason why he can spin the book is because they have already located where the center of gravity for the book is. Then you just keep spinning it. That's going to be gyro motion, right? Then you'll be balanced often. You know, see before when people spin the book? Yeah, that's the application of it. But you can do much more things. This is just one of the application of it. We're not looking to the center of gravity just to spin the books, yeah. Right. So yeah, this is things. Okay, guys, I don't think I can finish this here, but let me just give you a quick briefing on this, guys, so that you can do the homework and exercises at the back here, guys. I'll repeat this last part again next week because I only have 4 more minutes left. I only want to because I want you guys to know what's going on. In terms of the triangle method, it is essentially the same thing as the circular motion one, right? Like I mentioned, if there is one force here, AC attention. If I have one force here and another force here, I will always have a resultant force in between the two forces here. Okay, can you see that? Okay, one force here, always have a resultant force here. Okay, now today, if I want to identify how much this is, I can actually use the triangle method to determine how much is my resultant force. Let's say, for example, today, let's say, for example, today, I have one object here, right? And it's being put in this direction with 6 newtons, and it's being put in this direction with 8 newtons here. I want to find how much my resultant force is. I want to find how much this is, okay? I can use the triangle method by drawing up all my information, okay? If I want to draw it up, first and foremost, I need to know that this is going to be a triangle, right? If I just look at these two forces here, you know what students would like to do for me? They would like to do this. They'll say that, oh, because there's two forces here, this is going to be the triangle. Which is absolutely wrong, guys. Let me tell you why. Because if you have this direction as your resultant force, right, you're basically this direction or this direction, right? Meaning to say, for some God-forsaken reason, when you have one force here and another force here, you'll either have resultant force in this direction or resultant force in this direction. Listen up, it's impossible. It's impossible to draw a triangle like this. So what you should do is you should bear in mind the direction the arrows are pointing in. With that, if I want to formulate a triangle, I could either move the y-axis towards the right, which will make it look something like this, or I could move the x-axis bottom, which will make it look something like this. You'll notice that regardless of however way I rearrange it, all the arrows are still pointing in the same direction. This right here will still be right. This down will still be down. And this resultant force here will still be in the same direction. Okay, this is how you're supposed to formulate the triangle. Once you identify that, okay, this is the triangle I want, right? The next thing you need to do is just draw the scales only. Let's say, for ease of calculation right now, I say that 1 cm represents 1 Newton. It means to say I have to draw one arrow that is 8 cm downwards, one arrow that is 6 cm towards the right, and then I find the resultant force by combining this with this here. Okay, this will be my resultant force. I measure how long this thing is now. Let's say this thing is 10 cm, right? Then my resultant force here is going to be 10 newtons. You get what I mean now? This is what we call the triangle method. First, you need to identify where your forces are. You need to make it into the proper triangle, not the wrong one. Draw the scale and then draw the real diagram to scale up, to scale. Okay, so I'll repeat this again next week because we really don't have enough time, just for the sake of homework only. So this is what we call the triangle method. Today, if I have two forces here, I'll always have a resultant force. This resultant force is always in the same direction, regardless of however I rearrange the triangle. Okay, I'll do the first one for you guys. Then after that, you do the second one, and then everything else as homework. Guys, this one here is going to be homework. Pay attention to how we're going to do this one. Okay, look at A first. They say find the resultant force for two perpendicular forces, one that is 8 newtons towards the east is this direction, and one that is 6 newtons towards the south, which is this direction here. State the resultant force, right? So first and foremost, I identify that this is going to be the 6, this is going to be the 8, this is my resultant force. So this is not a triangle, right? And I can't combine it like this. So I'm going to make the triangle look something like this. This is 8 Newton, this is 6 Newton, and this is my resultant force. With this miniature diagram for reference, I'm going to start writing the scale. I'll write something like maybe 1 cm represents 2 newtons. Okay, then after that, I'll draw a 4 cm here, and I'll draw another 3 cm here. Okay, make sure they are perpendicular. Right, then finally, I just need to combine this part to this part here already. This is going to be my resultant force, which you will definitely find 5 cm. That means to say your resultant force is going to be 10 newtons. You get what I mean? Copy this down, and then everything else is homework, guys. Everything else from this 1.5 is homework. We'll discuss and do the answers next week. Okay. Show me a drawing first. Do you draw it correctly or not? Bro, this one is to scale, bro. This is the mini diagram. It's to scale. That one is 3 cm. To scale, 3 cm, 4 cm, man. Yeah, you're supposed to identify how much this is in the real exam, the resultant force. This is the reference diagram, Macy. This one is the reference diagram, so that when you draw this, you have something to refer to. You get what I mean or not? Is this scale?
Yeah.
Is it perpendicular? Okay, now I'll teach you this next week. Okay, guys, what I want you to do, attempt to do this one by next week, right? And finish all the exercises from here. Next week is going to be exercise week, guys. Next week is going to be exercise week. We're going to discuss the answers, and then we're going to do one more set of exercise before we proceed on with the chapter, guys. Yeah. Good. Oh, I missed your correct. Good. Okay, guys, if you have no questions, that will be it for today. But if you have any questions, you're more than welcome to stay back and clarify any doubts you have in your head.